All right, good morning, everyone. We're going to finish some of these examples for power rule, and then we're going to talk about trig integrals. And then we'll move to solving differential equations, and then being able to take the antiderivative multiple times to get from second derivative back up to the original function. Remember how first semester we're able to work our way down to the second derivative, and so now we need to be able to work our way back up the chain. All right, so to recap where we left off yesterday, we talked about how we have power rule for integrals as well, which is basically undoing the process that we did with derivatives. So instead of subtracting 1 and then multiplying by the exponents, we're now adding 1 to the exponent and dividing by the new exponent. Just like power rule for derivatives, we also have power rule conditions that are required before we apply power rule. So we need rational exponents to show up. So radicals convert to rationals. We need variables in the denominator to be moved to the numerator. And also we need our expression to be expanded fully. So if there's any variables that needs to be combined together, we need to do that. If we have any parentheses, we have to resolve those. So this is going to be the integral rule that you use the most, but we need to make sure that things are in place before we apply power rule. Number 4, we talked about how after we expanded, our terms are all going to rise by 1 degree, right? So x squared will turn itself into x cubed, x will turn itself into x squared, and the constant of 1 is going to turn itself into 1x. You see how all these degrees are rising by 1? 2 becomes 3, 1 becomes 2, and then constant becomes a linear. And again, the reason why that 1 goes to a 1x is because technically a 1 is considered an x to the 0 power. And if you go through power rule, starting with x to the 0 power, you add 1 to the exponent, so 0 plus 1 is 1, divided by that 1, and you get 1x. Right? So constant is going to turn itself into a variable and plus c. The last problem that we did at the end of class was number 5. So this was where we had to do all 3, we had to involve all 3 cleanup conditions here. So first thing that I did was convert the radical to a rational exponent. We know that this x to the 1/2 is out of place. We have to move this up to the numerator. So we're essentially converting this division problem into a multiplication problem. So to ensure that we are keeping track of what needs to happen, I'm putting this x plus 1 in its own set of parentheses so that I can clearly make this into a full multiplication problem. The x to the negative 1/2 needs to multiply fully with the x plus 1. But as I do that, I have to resolve this parentheses. So distribute the x to the negative 1/2 through by adding exponents. So 1 minus 1/2 is positive 1/2. And once we have our expression ready for power rule, then we apply power rule. We add 1 to the exponent. So 1/2 plus 2/2 is 3/2. So whatever exponent we have, we're going to copy that value below. Negative 1/2 plus 2/2 is 1/2. Copy that value below. And then our final cleanup that we need to do is to flip these fractions up to the numerator and take the reciprocal. So I have 2/3 as my first coefficient and then 2 as my second coefficient. And then don't forget plus c. Okay, any questions so far with power rule? Okay, let's look at number 6. I'm going to put this on a separate sheet here. So number 6, same idea. We have to do a little bit of cleanup before this expression is ready for power rule. So first thing is I'm going to rewrite this radical as a rational exponent. Make that square root of y to the 1/2. Next up, I'm going to try to merge these together. So add exponents. 1 plus 1/2 is 3/2. And all the meanwhile, I'm just cleaning up. So if I'm just cleaning up, I'm not doing any calculus just yet. So these integral and dy notations will have to be continually repeated and rewritten. But as soon as we apply power rule, then these notations can drop out. All right, something is still out of place. This y to the 3/2, I'm going to make this go up to the numerator, as we need all variables in the numerator. Okay, so now we're ready for power rule. All right. So I'm going to get ready for power rule. I'm going to add 1 to the exponent. So plus 1, in this case, the same thing as plus 2/2. All right, so I'm going to apply power rule. The 3 is the coefficient that's going to stay in front. Add 1 to the exponent. Negative 3/2 plus 2/2 is negative 1/2. Once you have that exponent, copy that same value below. So this is our answer. We just have to do a little bit of cleanup after this. So take the negative 1/2, flip it up as negative 2. And also I'm going to push that negative y to negative 1/2 back down to the denominator. So once this negative 1/2 gets pushed up, it becomes negative 2. 3 times negative 2 is negative 6. And then finally, I'm going to move that y back below. And you can either leave it like this, or if you want to convert it back to a radical, that's fine as well. Either way is fine. Just no negative exponents. Okay, any questions with 6? Okay, number 7. I'm going to put this on a separate sheet, give myself room to work on this as well. All right, so number 7. So this, the cleanup effort here is quite extensive. A lot of things we need to do before this is even ready for power rule. So rational exponents, I need to convert these radicals. Variables in the numerator, so this cube root of x has to eventually find a way to come up to the top. And expansion, so I have to fully expand all my parentheses and eventually distribute. So I'm going to look to do a couple of things at once. I'm going to convert these radicals. I'm going to start foiling this out. So 1 minus x times 1 minus x. Which becomes 1 minus 2x plus x squared. So I took the results of this foiling process and put it here. Radicals converted to rational exponents. All right, now from here, you may be expanding your expression in a different order than me, which is fine. But for me, I'm just thinking I'm going to bring this x to the 1/3 to the top. And if I can bring that x to the 1/3 to the top, then maybe I can find a way to merge these together first. And then once these two, because the thing with multiplication is I kind of rearrange and I can combine in whatever order I like. So if I just move this x to the negative 1/3 here, combine these together, and then I can just spend just one time distributing through rather than multiple times. So that's just my way of trying to reduce the amount of work. So I'm going to put these two together so I can combine them first. And if I merge these together, I'm going to be adding exponents. So 1/2 minus 1/3 is same thing as 3/6 minus 2/6 if I want to find common denominators. Or you just make the calculator do the work for you here. So that gives me 3x to the 1/6. Right. So because I combined those two things first, now I can just spend my effort to distribute, and I only need to do it once. So as I distribute through, I'll add exponents. 1/6 plus 1 is going to be 7/6. 1/6 plus 2 is the same thing as 1/6 plus 12/6, which is 13/6. And all the meanwhile, my integral and dx notation is still going to be reappearing because everything that we're doing is still just algebraic cleanup. All right, so now it looks like every term is ready, right? We've spent all that effort to get to the point so that we can apply power rule now that all three conditions have been met. So I'm just indicating that I'm adding 1 to the exponent, just matching my denominator to make it easier to see what is going to come of it. So this will become 7/6, 13/6, 19/6, and as I apply power rule, now my next step, my integral and dx notation would go away because I'm taking the antiderivative. Okay, coefficient stays out in front. My exponent is copied down below. Flip those fractions up, make it 6/7, make this 6/13, make this 6/19. And then finally, I'm just going to do a little bit of cleanup with my coefficients here. All right, any questions with our integral, our antiderivative? Okay. Let's go to our next page. Trig integrals. So these integral rules, we learned first semester. And the idea here is that these integral rules are just going to be undoing these derivative rules that we learned or that we used first semester. So let me just kind of go over how we're not really learning any new rules. We're just going the opposite direction. So we have all these derivative rules, right? Sine becomes cosine, tangent becomes secant squared, secant becomes secant tangent. Okay? And then all these trig functions that starts with c, they all produce negative derivatives. Now imagine us going backwards here. So if my derivative of sine is cosine, then that means my antiderivative of cosine should bring me back up to sine. So that's exactly what's happening here. The integral of cosine is just sine of u plus c. And just think of u as x for now, and we'll see how the u is going to play a role as we look at more complex problems. But I just want you guys to see that pattern here. So tangent derivative of secant squared, which means that the antiderivative of secant squared should bring me back up to the tangent level. And so that's what this rule is telling us here. Okay, secant's derivative is secant tangent, which means that the antiderivative of secant tangent must bring me back up to secant. And that's here. Okay. Because cosine is negative sine, so that means if I want to take the antiderivative of a positive sine, then this negative has to go somewhere, so it's going to go with the cosine. So the antiderivative of sine is going to be a negative cosine. Cotangent produces negative cosecant squared, so the antiderivative of cosecant squared is going to bring me back up to a negative cotangent. And that's the rule here. Cosecant is negative cosecant cotangent, so integral of cosecant cotangent, this negative is going to have to go somewhere, so it's going to attach itself to the cosecant. Right. So here we're just applying these integral rules, but sometimes we may have to rearrange something that doesn't quite look like the rule to make it look like the rule before we can apply it. So if you look, tangent, cosine, there's no rule that matches perfectly with this. So maybe I can do a little bit of rearranging here. What if I think of tangent as tangent times 1 over cosine? And these are the same things, right? I'm just pushing that cosine out in front just to see if I can get it to look like a different form. And if you think in terms of what else I can represent 1 over cosine, 1 over cosine is same thing as secant, because secant and cosine are reciprocals of each other. So I can rewrite this as tan x secant x So tan x secant x, just replace the u's with x's. We have a perfect rule that matches here. And then sine, we have a rule for sine as well. Okay, so secant tangent becomes secant. Sine becomes a negative cosine. We got to keep track of our multiple negatives here. Two negatives become positive. All right, number 2, we have sine x over cosine squared x. What if I split that cosine squared x out? Just seeing if, because right now this doesn't match any of the rules that we have. So maybe I can just create a different variation of this problem. And if I think of this as sine over cosine and 1 over cosine, then we can kind of see some patterns come out, right? Because sine over cosine is same thing as tangent, and 1 over cosine is same thing as secant. So really, we're able to see that This is also tangent secant. And because we're able to kind of rearrange it into different form, we're able to make it match. All right, number 3, 1 plus cotangent squared x. If you look, we don't have a rule for cotangent squared, but we do have a trig identity that says 1 plus cotangent squared x is the same thing as cosecant squared x. And I can just make a clean substitution here. And we do have a rule for cosecant squared, which is negative cotangent. Okay, questions here? On the quiz review, I put all the rules from 4.1, 4.2, and 4.6 all together. So I'll also have that formula sheet attached to the quiz as well. So everything that you need will be on the formula sheet. All right, next page. All right, differential equations. Differential equations are simply equations that involve derivatives. We're going to get into this a lot more when we get to chapter 6, but right now we're just going to get our feet wet, kind of be introduced to the notations, and then when we get to chapter 6, we can kind of build off of something that we've seen at this point. So anything that is has an equal sign, and anything that has a derivative form like y prime or dy dx, that just means that we call these differential equations because these are sitting at the derivative level. And solving differential equations, that just means that we're taking a derivative and moving up a level to the original function. So we're just basically taking the antiderivative. It's just another way of saying we're going to take the antiderivative of an expression, is solving a differential equation. So here are the steps. We're going to first rewrite y prime as dy dx. These mean the same thing. It's just that dy dx is a more descriptive form of y prime. And this is going to help us with matching the notations that we want to see. Okay, second step is separate the variables on either side of the equation. So we want the y's and dy's on the left side of the equation. Of the equation. And then we want the x and dx on the right side of the equation. After that, we'll take the integral of both sides. And then we'll solve for c if we need to, if it's asking for a specific solution. All right, so let's look at example 3. Suppose y prime is equal to 2, solve for y. So let's rewrite y prime as dy dx. I'm going to separate the variables. So I want the y's on the left side. I want the x's on the right. So I'll just go ahead and multiply this dx over to the right side. Once we have our variables separated, then we'll take the antiderivative or integral of both sides. I'm going to put a 1 here, so just to kind of help us see what's going to come out of that. Let's start on the right side here. What do you think is the antiderivative of 2 dx? Good, 2x. Remember, integral and dx is just notation, and we're just taking the antiderivative, so every term is going to rise by a degree of 1. So here, there's no x's, so when we take the antiderivative, an x is going to appear. Let's make sure we understand that this is not derivative, right? We don't make this go to 0 because that's derivative. Antiderivative, all our degrees are going to rise by 1. So we know the right side is going to be 2x. And the left side is integral of 1 dy, so we're taking an antiderivative of 1 with respect to y. So what do you think is going to come out of this one?
Y.
Yeah, becomes y. So this tells us I'm doing everything in terms of y here. This tells us I'm doing everything in terms of x. So we get y is equal to 2x. Now, technically, both sides are producing their own set of constants. So there's a constant here. There's another set of constant here. But instead of writing plus c twice, we're just going to merge all the constants together. So imagine you're subtracting a constant over, and we're just calling the combination of constants as just a plus c. So rather than writing out twice and keeping track of different constants, we're just going to merge them all together and say, okay, a plus c is just going to be written once. Instead of keeping track of multiple constants, we'll just merge them together. So we call this our general solution. General solution because we don't have a specific value for c, we just have a family of functions to represent our solution. All right, any questions so far? Same idea with 4. Go down our steps here. There's no need to rewrite because our dy dx is already showing for us. We're just going to go ahead and separate our variables. So I'll move the dx over to the right side. Take the antiderivative, take the integral. I'll put a 1 here just as a reminder that that 1 is going to have to transform. Okay, go through power rule. Right side becomes x to the 4th over 4. And then 1 is going to turn itself into y. Again, this is a general solution because we have a plus c showing. Any questions here? All right, example 5. Now we're going to be solving for a specific solution. So specific solution just means that we're going to go one step further past the general solution. That means we're going to be given some order pair that can help us solve for c. And once we have a numeric value for c, we'll update the equation. And once we replace the c with a number, then we've changed our general to a specific solution. But if it's asking for a specific solution, we're going to do the same things initially. We're going to try to get to our general solution, and then from there, decide what to do from there. So we'll go through our steps the same way. Y prime, let's rewrite it as dy dx. We'll go ahead and move that dx over to the right side. Take the antiderivative. I'll put a 1 to kind of as a placeholder. My variables are nicely separated. Everything involving y's on the left side, everything involving x's on the right side. Okay, power rule for every term. This is going to be in terms of y, so I get y. 2 terms, so apply power rule twice. 4 becomes 4x, and then we just have to write plus c once. So we've arrived at our general solution, or general equation. So to move from general to specific, we're going to involve the order pair. So we're going to plug in 4, 10. Four goes in for x, 10 goes in for y. Clean this up. We get 16 over 2 is 8. 8 times 3 is 24. C is equal to 2. So now we'll take this value and put it in for the C. And now we're going to be able to update from a general to a specific solution or a specific equation. Any questions here? Okay, last page. First semester, we were able to start with our function and take the derivative to get to f prime, take the second derivative to get to f double prime. And now we're going to go the other direction. We're going to be able to move from second derivative back up the chain to the original function using power rule for integrals. Now, as we go through these notations, we're just going to, we don't have to do integral notation on the left side. This is just to kind of help us begin to have this in our heads. So when we get to more complex problems in chapter 6, we're going to at least be able to recognize the fact that we may have to do a little bit of work on the left side. But right now it's just kind of really easy. Integral of 1 just becomes y. But on this side, let's just go ahead and leave everything in terms of f double prime or f of x. So the left side, we'll just go back to leaving them as notations. So I'm starting at the f double prime level. And I'm going to move up the chain to f prime. So I'm going to indicate that my derivative is going to be the result of taking the antiderivative of 6x plus 4. So 6x plus 4 is currently at the second derivative level, but I know that through this process, it's going to allow this to transform into an expression that is sitting at the f prime level. Okay, so apply power rule. Okay, so we're halfway there. We're able to move from f double prime to f prime. And we want to find our specific solution. So let's see, do we have anything that is available for us to solve for c at this point? We have two ordered pairs. One's at the function level, one's at the derivative level. So it looks like this is suitable for us to use to solve for c at this level. Let me write this. So I'm going to put 3 into the f prime slot. I'll put 0 in for the x's, and that should allow me to solve for c. The zeros will go away. I'm left with c equals 3. And I'm going to use this value to update my f prime. Now that I'm sitting at f prime level, I'm going to take the antiderivative again, and that should bring me up another level to my f of x. So once I go through this procedure, it'll convert this expression to the f of x level. Power rule. And because I'm producing another constant within the same problem, we typically like to use a different constant letter. So sometimes I see students using c sub 1 and then make the second one c sub 2, but I'm going to just make this a plus k. That's usually the common letter that is used if you're having to apply, or if a constant shows up twice in the same problem. So now I have a general equation at the function level. Can I solve for this constant? So I have another ordered pair that is at the function level. So this is now, I can use this to help me solve for k and update this general to a specific solution. So I'll put 5 in for f of x. I'll put 1 in for all the x's, and that should allow me to get that k value. And while I'm at it, I'm going to start to try to reduce this as well, clean this up. One plus 2 is 3, 3 plus 3 is 6, 5 minus 6 is -1. So now that I have a k value that's -1, I can go ahead and replace my general equation, my k, with -1, and update my general to a specific equation. I'll put this down here. All right, so -1, yeah, so x cubed. All right, any questions with 6? All right, one last one, number 7. We have second derivative, 12x plus 6. We're going to make our way back to up to g of x level. So we start off here. I'm going to indicate using integral notation that I'm about to take the antiderivative, and this process will bring me up to the g prime level. All right, so we go through power rule. Clean this up. 6x squared plus 6x plus c. Now I have a c here. I eventually want to solve for c, but can I solve for c at this point? Do I have an ordered pair that I can use here?
No.
Not yet. That's right. Not yet. We have 2 ordered pairs, but they're both sitting at the g of x level. So what that means is we got to hold on to this c a little bit longer than what we had to do in the past. So we'll take the antiderivative of this expression. I know it seems kind of strange taking the antiderivative with that c still sitting there, but treat c like you would if it was a constant, like a 3 or a 5 or 8. Just imagine that there's a number sitting in that slot. So we'll take the antiderivative. 6x squared becomes 6x cubed over 3. 6x becomes 6x squared over 2. What do you think the c is going to turn into?
Cx.
Say it again.
Cx.
Yeah, cx. Good. Right. If it was 3, you would say 3x. If it was 5, you would say 5x. So same thing, c, which has become cx. Now, this process is going to produce its own constant. So we're going to have a plus k that shows up here as well. All right. We took the antiderivative twice, so we're going to have 2 constants. It's just that the previous problem, we're able to resolve that c halfway through, so we didn't have to have that c show up at the end. But in this case, because our order pair is not ready for us to plug in, we have to hold on to our c value, so it looks a little messier here. So that leaves us with 2x cubed plus 3x squared plus cx plus k. So now we have 2 order pairs that we're going to be using to solve for c and for k. But one of these is going to be easier to start with. Which one do you think is going to be easier to use to solve for one of the constants?
G of 0 is equal to 4. Solve for k.
Okay. Why is this an easy one to start with?
Because it turns the c of x into 0.
Yeah, so the nice thing with 0 is that it's going to wipe out a lot of things, and it's going to allow us to isolate one of the variables or one of the constants much faster than this, right? So anytime you're picking between 2 order pairs and you're having to solve for 2 different variables, you know that the 0 is going to be the one that is usually going to be the more useful one to begin with. Okay, so we'll use that 0, 4. So we'll put 4 in for all the y's, and we'll put 0 in for all the x's. All right, so that 0 is going to wipe all these terms out, isolate the k, so now that we have the k value, we're going to go back to our general equation, and we're going to update the k with 4, and now that will allow this second order pair to plug in nicely, and we can solve for c. Okay. So I took care of the k constant, and now the second order pair, I can use this to solve for c. So -2 goes in for my g of x, 1 goes in for all my x's. -2 equals 2 plus 3 plus 4, that's 9. Subtract 9 from both sides, I get c is equal to -11. And now I'm just going to rewrite my g of x and replace my c with -11. All right, any questions here? Good. So we've worked our way to the end of our notes, end of our new material. We'll have tomorrow and Thursday to do quiz review, and Friday will be your quiz. I'll have a help session tomorrow morning and afternoon. Both will be recorded. So if you have any questions or if you have any specific things that you want me to go over, we can go over that. All right. All right. Thanks, guys. Hope you guys have a great day. See you tomorrow.
Thank you, Ms. Yang. Have a nice day.
Thank you. You too. Bye.
Thank you.
Bye.